Light has a paradoxical nature. Does light consist of waves, or does light consist of particles? How many think that light is like waves? Is he show of hands? Anyone who feel that way? Okay, about 30%, 20%. How many feel that light is a stream of particles? Okay, that's about 2/3. You're both right, depending on who's looking. You see what I mean? We'll talk about the velocity of light, and this is kind of fun, because when I gave my study of Genesis a decade or two ago at Calvary Chapel, I mentioned then that light was not a constant. And some of my dearest friends, who are very, very expert in Einstein's theory of relativity, one of the guys that came to the Lord in my first Revelation study at my home many years earlier, a dear friend. And also he's chairman of a ministry that is a prominent apologetic ministry, in which the leader's a very, very bright guy. They're both physics sophisticated people. And they took me apart privately. Chuck, you got to understand, light's a constant. I really took a lot of abuse for this, because I banked on Barry Satterfield and some papers that had just come out about that time. And it amuses me, because I'm going to give you the same material I gave then, but I can give it to you confidently now, because suddenly in the last couple of years, the physics community has finally discovered, guess what? The speed of light's not a constant. So I'll talk a little bit about that. And I'm going to give you an analogy of holograms that I think you might find interesting. But let's talk about the central paradox of light. Sir Isaac Newton, of course, is probably without peer in the history of science, 17th century. He viewed light as a stream of particles. And he had reasons for doing so. And because he did, everybody did. It was a follow the leader kind of thing, right? A guy that was about 13 years older than him, Huygens, developed a wave theory of light, because from the fact that light can be refracted and reflected implies it acts like waves. But he was not really listened to, because everybody listened. Sir Isaac Newton had the insight on truth. There are a couple other guys, Leonard Euler and Ben Franklin, were also ignored until two developments occurred in the early 19th century. Euler was the father of geometry, trig, calculus. He discovered the imaginary square root of -1 integration. He's a very, very, very prominent mathematician. And of course, Ben Franklin was quite a broad Renaissance kind of guy too. But we had wave discoveries. A guy by the name of Thomas Young conducted an interesting experiment called the two-slit experiment. I'm going to show you what that is, because it totally shattered the scientific world at the time, and still does to anyone that hasn't really studied this. The two-slit experiment, which demonstrates the wave, that it's really a wave-like thing. A guy by the name of Fresnel, his experiments are more complete, and he concluded also that that light behaved like waves. The Fresnel lens was designed for lighthouses. He designed lenses that were that light would come out parallel, if you will, in effect. And this is all about the time of the Napoleonic Wars and so forth. So, Young, by the way, is an interesting guy for lots of reasons. He made contributions in science and capillary actions, elasticity. He's also the one that was monumental in deciphering the Rosetta Stone and hieroglyphics. The people of that period were incredibly broad gauge. That's why I use the term Renaissance man, I guess. Now, see, Newton was knighted in 1705, and he died in 1705, and died in 1727. So it was still too early to dethrone him. I mean, he had his views, and people would be very reluctant to examine evidence in view of those views. We got to be careful ourselves, because most of what we've been taught in school is wrong. And how many of you would take a physics class with 1950 textbooks? I wouldn't, I mean, I did, but I mean, you stop and think what's happened in 50 years, almost everything that was in those textbooks has been disproven. If you take current textbooks, they're still full of known lies and deceit. And that's one of the great tragedies in our education system. But let me talk a little bit about this two-slit experiment to give you an example. On the left, we have, say, a partition with a slit in it, a little light. Light can come through that slit, and that light can then hit an image, a piece of a wall or a piece of film or what have you. And if you plot the intensity of that light, obviously in the middle is the brightest, and it tapers off. It follows something approximating a Gaussian distribution. That's all pretty straightforward, no problem. Well, if you have if you put between that slit and your plane, a plane with 2 slits in it, well, you'd expect the light that hits it, let's just cover up the bottom one and look at the top one only. It will act like a point source of light, and you'll expect, of course, the distribution of energy to be just like the previous one, right? If you cover that one up and do it the other side, you'd get another one. You would expect that if you opened both slits, you would get the sum of those 2 slits, right? That would seem reasonable. If you open both slits, though, you don't get the sum of those. You get something very different. You get the interference between the 2. Mathematically, you don't get just h squared plus h squared plus j squared. If you use h and j for the 2 slits, you get h plus j squared, which spreads out to give you h squared plus j squared plus a whole other term. And it's the most powerful term it's the middle one. It's the interference. So what this slit means is, see, this makes no sense the more you think about it. If light is a stream of particles, and it's going through one of these slits, it appears to know whether the other slit's open or not, because it'll behave differently. Follow me? See, it's obvious that the individual particles are not operating individually. They're operating organically as a group. And that creates a real mystery, because on the one hand, light can be demonstrated to be a stream of particles. It also behaves like waves, both. And that created all kinds of problems. The 19th century, of course, reversed. A guy by the name of Foucault, the guy that did famous for the pendulum, he made a discovery that shook the world at the time, that the speed of light was less in water than in air. Well, that's no surprise for wave theory people, but it makes no sense for the particle people, the corpuscular theory. Because if it slows down, what speeds it up again? Are they pushing from the back? I mean, you try to deal with that mathematically, you have real problems. So that created all kinds of stir. Then this incredible human being, James Clerk Maxwell, comes along, and he's discovered many, many things, but he's primarily responsible for our whole awareness of what we call today the electromagnetic spectrum. And he discovered, among other things, that the light is an electromagnetic wave. So it not only acts like a wave, it acts like a wave in some very profound ways. And a contemporary of that time, Heinrich Hertz, established electromagnetic transmission and reception as a result of all that. So now we get to the 20th century, there's a whole reversal. And then there's this weird experience in 1900. A guy by the name of Max Planck was wrestling with what they call the black body problem. I won't get into all that. But he was trying to get a mathematical description of what was being observed. And out of desperation, having tried everything else, he misapplied a couple of Boltzmann's equations, and he applied them incorrectly. And they worked. They really shouldn't have. But in doing so, he discovered what the implications of the experience, and I won't get into all the math here, is that it wouldn't integrate because light comes in little bundles. So it's not continuous. It's in quanta. And so the mathematics revealed a non-continuity that was operative here. It was a few years later that Einstein published the explanation of what Planck had encountered. And it leads to a revival, again, not only the corpuscular theory of light, it opens the door to the field that we call today quantum physics. The fact that the subatomic particles behave in the strangest ways. And it's so strange that Boltzmann, who understood the real implications of what they discovered, couldn't handle it. He committed suicide. It so shattered their understanding of reality. And we'll talk about the quantum physics next time in more detail, because there'll be some reasons for it. But the main idea is that energy is not continuous. It comes in little tiny bundles. That was the discovery. What they've discovered since is that length, mass, energy, time itself is quantized. It's in digits. The analogy is like a piano. You can hit a key, you can hit the key next to it, but you can't get a sound between them. You with me? It's really digital in a sense. Do you follow what I'm saying? It's quantized. Well, so is light. It's quantized. So is everything quantized. And we discovered today, you and I are in what could properly be called a digital simulation. Not analog, not continuous. It's very strange. And we'll get into that next time somewhat. So this opens the door to the whole paradoxical world of quantum physics. And the chief player here is the photon. The corpuscle, it's this unit of light. You know, it's fascinating when you stand backwards. In 1906, J.J. Thomson, very, very prolific scientist, got the Nobel Prize for proving that electrons were particles. No problem. What's interesting is his son in 1937 was awarded the Nobel Prize for proving that electrons were waves. So each of you that raised your hands during my questions was correct. But the really bizarre part of this, you see, the wave-particle duality, as they call it, is a central paradox in quantum physics. And let me just give you a glimpse ahead. There's now compelling evidence that the quanta only manifest themselves as particles is when we're looking at them. And you think, and I'm not joking, we'll talk a little bit about that next time, because it will alter your whole understanding of what you and I call reality. And that's where we'll get into that, because it all impacts our understanding of the first chapters of Genesis. Let's shift to another subject, the velocity of light. In the 17th century, Johannes Kepler, the famous astronomer, René Descartes, the famous mathematician, and their following, of course, believed that light was instantaneous. They felt that light, its speed was infinite, that light traveled instantly, and that was the sacred dicta. Until 1677, a Dutchman by the name of Olaf Romer, he measured the elapsed time between the eclipses of Jupiter with its moons. He noticed that if you measured the eclipse of the moons at Jupiter, you'd get about a 15-minute difference depending on where you were on the orbit. If you did it certain times of the year, it would be different. And he began to realize that those distances were such that if he did this cleverly, he could actually measure the speed of light, which he did. And he found out, first of all, that light had a finite speed, a very high speed, roughly 300,000 meters per second, or 186,000 miles per second, as we would say it. But the main point was it was finite. That shook everybody. No one would believe him. He had his data. The physics were something else you need to understand. Scientists like to brag that they're objective. That's baloney. That's utter baloney. They cling to their presuppositions with the same tenacity that we all cling to our prejudices. It takes an abundance of evidence and effort to get these incorrect notions unseated. And Romer's experiment was repeated 50 years later by James Bradley, an Englishman. He confirmed Romer's work, and finally they began to acknowledge, gee, yeah, maybe light is not instantaneous, it has a finite speed. So that was the big breakthrough. Over the last 300 years, light has been measured 164 times at least by 16 different methods. And I thought I'd take you through each one, right? No, of course not. Two guys, Barry Setterfield, a dear friend, an Australian, and Trevor Norman, a mathematician, were troubled by something. By the way, Barry Setterfield is one of the most deeply committed, practicing Christians I know. And he was wrestling with the whole problem, a certain problem in physics, and he took it into prayer, as he describes it. How could this be if light is a constant? It was almost like a voice says, who said it's a constant? And he suddenly realized that he was down a blind alley because he was in a situation to solve this problem. He'd have to challenge the idea, is light really a constant? So he and Trevor Norman decided to collect information. They went back and were able to dig up the raw data from these experiments through the centuries of the measurement of the speed of light. In 1677, when Romer measured the Io eclipse, his conclusion was that that the speed of light was about 307,600 kilometers per second, with an error range of about 5,400 kilometers per second. Okay, not bad in view of those times, of course. In 1875, Harvard, using the same method, repeated the experiment, and because of better technology over more than 100 years, they had a lower error band. Instead of 5,400 kilometers per second, it was down to 13 kilometers, give or take. You follow me? And then in 1983, The National Bureau of Standards, using a laser, ran their experiment, and they got the error down to 0.00003 kilometers per second. So as you look through the couple of centuries here, you realize that the technology is improving, the error band is getting much more precise. But that's not what caught Barry Setterfield's eye. What disturbed him is look at the mean. It went from 307,600 down to 299,921, then down to 299,792. It's the speed is slowly decreasing. It's actually getting asymptotic. A mathematician by the name of Alan Montgomery took all the data and subjected to a rigorous computer analysis and came to the conclusion that the regression, not just of these three experiments, I just give you three to give you a summary, that if you look at all the data, there's a 99% correlation to what he called a cosecant squared curve. In other words, if it's going slower now, it went faster in the past. How much faster? Somewhere between 10 and 30% faster in the time of Christ, somewhere about twice as fast in the days of Solomon, somewhere about 4 times as fast in the days of Abraham, and about 10 million times as fast prior to 3000 BC. Now, this, of course, it was started to be published here over a decade ago, was given the horse laugh by all the classical physicists. Who are these characters, and don't they understand the speed of light? Everybody's been in physics. The more you know about physics, the more you've been into atomic structures, you discover the speed of light is a factor on almost every equation you get into, in terms of energy transfers and on and on. The speed of light's a very fundamental parameter. But that's the point, it's a parameter, not a constant. And so the idea that it's not a constant shook them. But even Einstein expressed surprise during his lifetime that anything would be constant in the universe. He accepted it as a constant, but reluctantly, because he withheld some disbelief. So this, first of all, pulls the rug out from under any reckoning of time. You're talking radiological time, or you're talking orbital time. See, suddenly you're raising some serious questions here. And in the first 6 days, let's rephrase that. In the first 5 days of the creation week, who was around? Only God. So I'll take him at his word. Okay? So, and this is why more and more scientists are beginning to accept the many evidences in many fields of science that the Earth is actually far younger than most people have any idea. Less than 10,000 years, not millions and millions and millions. Now, we went through a few of those last time. We'll give you some others before our series is over. Now, there are other confirmations here. This kind of thing was mentioned in French Astronomical Journal in 27. Tom Van Flanderen in the U.S. Naval Observatory points out that atomic clocks are slowing relative to orbital clocks. I'll come back to that in a minute. A guy by Trotsky in Moscow, independent of Setterfield, about the same time, published back in '87, a similar kind of insight. And there have been other. Now, I'll tell you what really bothers me. In the last 18 to 24 months, there have been literally dozens of articles in the reputable journals, Nature, Science, the highly reputable journals, by different guys who've discovered the speed of light's not constant. What frosts me about watching this parade, on the one hand, I'm gratified to see that we're not out in left field with some weird idea that this is now becoming accepted. But I find it significant that none of these guys have had the integrity or the character to acknowledge Barry Setterfield's original papers. The abuse that he had from the profession for more than 10 years, you'd think would at least merit a reference. But there are none forthcoming. There are now articles around that betray that, and there's plenty of the stuff on the internet for those that are interested. This atomic versus orbital time, see, before 1967, the second was defined as a very, very small fraction of one Earth orbit around the sun. I won't bother with the decimals here, but you get the idea. In 1967, they redefined the second to become a certain number of oscillations of the cesium atom. So the definition of 1 second got nailed from the one system to the other. You follow me? And so that means that all the measurements of time since '67 are done in atomic terms, not in orbital terms. You with me? Well, they've also discovered something, or Van Flanderen at the observatory points out if atomic clocks are correct, then the orbital speeds of Mercury, Venus, and Mars are increasing. That can't happen, of course, because where's the energy coming from? So the opposite must be true. See, if the gravitational constant is truly constant, then the atomic vibration and the speed of light are decreasing. And so, you see, if a planet's orbital speed increased, it would violate the law of conservation of energy, the first law of thermodynamics. If the atomic clocks are correct, the gravitational constant should change, and no such variations have been detected. So this is, if the atomic frequencies are decreasing, then 5 properties of the atom, such as Planck's constant, should also be changing. And statistical studies support both the magnitude and the direction of this change. So there's 4 out of 5 of the properties of the atom are confirming the idea that the speed of light is slowing down. It has profound implications for science. It has drastic implications for our understanding of the universe. And that's why I'm dragging you through this. Something else you've all heard about, the red shift. I'm sure if you've done any reading in technology, you know the idea that stars have their light shifted to the red. That's called the red shift. If you look at the spectra, it shifts slightly to the red. And so a guy by the name of Edwin Hubble in the 20s postulated that the ones that are furthest away are shifting most to the red, so he assumed that it's shifted to the red because they're speeding away from us. So the red shift in the star spectra is treated as an evidence that the universe has been expanding. That's where we get the idea of the expanding universe. That's why the Hubble telescope is named after Edwin Hubble, because of what they call Hubble's law. The more it's shifted to the red, the further away it is. That's been the dictum of, if you take a course in astronomy, at whatever level in college, that's what they'll teach you, the basis of Hubble's law. Well, there's a couple of guys, one in Germany, Halton Arp, and one in the University of Arizona, William Tift, have taken upon themselves for 20 or 30 years of collecting data on red shifts. And that was their area of professional interest. And they particularly cataloged what they call aberrant red shifts. Some of the stars aren't moving away, they're moving towards us. So they try to collect the ones that aren't following the rules, so to speak, right? But William Tift has discovered something rather shocking. As he analyzed the data, he discovered that this red shift always is a multiple of a number. In other words, it can't be anywhere. Again, it's like piano keys. It'll be at some number, an exact multiple of a certain constant. It's quantized, in other words. And he didn't bring any conjectures, he just reports the data. But there have been scientists who take that data and start analyzing it, and they've discovered something really interesting. They can explain the red shift, not by the rate at which the star is moving away from us, but by the change in the speed of light as it impacts atomic behavior. Since the orbits of electrons are fixed places, and so the speed of light changes, these certain subatomic phenomena will occur in discrete steps. And those discrete steps can account for the red shift. So it's not conclusive yet, they're still researching this, but it's very possible the whole idea of the red shift being evidence of expansion is suspect at this point. And the red shift is another strange confirmation that the speed of light's been slowing down.